Okay, hello everyone. Welcome to Applied Econometrics 1. This is Dr. Gallenstein, your professor, and this will be Lecture 1, the first lecture of the class. So I'd like to welcome you to the class. I'm really happy to have you with us this year. Okay, so Lecture 1. In Lecture 1, what we're going to do is we're going to look at data. We're going to calculate some descriptive statistics. We're going to talk about correlations. We are going to open up Stata, the statistical software that we'll be using in the course, and begin to look at a data set. This will also constitute kind of a review of some statistics that will lay a foundation for the rest of the course. So let's go ahead and get started. Kind of a more systematic review. We're going to start with a review of data types. Then we're going to look at our data in Stata. We're actually going to open up a data set and look at it. Then we're going to do a statistics review. And we're going to conclude with calculating some descriptive statistics in Stata. Okay. So let's talk about just what data is. This is kind of an example, kind of a stylized example of a data set. What you'll find in a data set is you'll find a number of columns and a number of rows. Each of the columns represent what's called a variable. A variable is some mathematical expression that can take different values. So in this particular data set, we've got a variable y and we've got a variable x. We can think of, let's say that y is income and x is education level. Okay, and then our rows, they indicate different observations. Now this might be an individual or it might be a household. Those are common ones that we'll see in this class. Let's say right now that each observation is an individual person. So then this would be an example of a data set of 3 people, and we have information on the income and the education level for each of those 3 people. This would be like we walked outside and we found 3 people walking around on campus, and we just asked them, okay, what's your income? And then what's your education level? How many years of education do you have? Okay, so let's just kind of go through this a little more. So the first row, this is person 1, the first person we talked to. Person 1 has an income of y1, some value of the variable income. And they have education level x1, some number of years of schooling, some value of the variable x, some value of the variable education. Same thing for person 2 and for person 3. So this is just basically what data looks like. Now we're going to be very interested in variables. We're going to be interested in how variables relate to each other. And variables can take a bunch of different forms. So let's talk about that. Let's talk about the types of data. So some of the most common types, and I'll be a little bit more structured in a moment, but some of the most common types that we're going to look at in the class will be continuous variables, binary variables, and categorical variables. A continuous variable is a variable that can take any value within a given range. A good example of income could be, actually, if we go back to our prior example, income. People could make any amount of income from 0 to infinity. So it's continuous. Okay. A binary variable, however, a binary variable is when it can take only one of 2 values, usually 1 or 0. We use binary variables to indicate for whether or not people have or don't have a particular characteristic. We'll see more on that in a moment. And then a categorical variable. A categorical variable is a variable that has a number, usually a number, or sometimes it can just be a script. We'll see that later as well. It usually has a number, so we'll talk about that. It has a number, but the number doesn't mean anything. The number itself doesn't mean anything. The number is just a label for something. So let's use an example. Imagine we're collecting data on farmers, and we want to know what crop they grow. We could have a data set that indicates to us the type of crop that each of the farmers in our data set, what type of crop they grow. And we can use numbers to label those different crops. So for example, we could say the crop variable equals 1 if the farmer grows maize. And the crop variable equals 2 if the farmer grows rice. The 1 and the 2 as numbers don't matter. They just matter in the sense that they're labels for the type of crop. Okay, let's get even a little bit more systematic here. Let's break this down into some categories. So if we have data, data falls into two broad categories: categorical, which we mentioned, and quantitative. Okay, let's look at categorical data first. Categorical data, like I mentioned before, consists of names or labels, even numeric labels, that are not numbers representing counts or measurement. Like if I said maize equals 1, rice equals 2, the 1 and the 2 themselves don't matter. They're just labels. They just represent things. Now you could have two different kinds of categorical variables. You could have a nominal categorical variable or an ordinal categorical variable. A nominal categorical variable is data that consists of names and labels or categories only. It cannot be arranged in some sort of ordering scheme. You can't put them into any particular order. An ordinal categorical variable would be one that has a specific order, a meaningful order. Let's just take a look at some examples. So nominal versus ordinal. So an example of nominal would be the crop example that I mentioned earlier. It doesn't matter what order they're in. Let's imagine we go and we collect a data set. It says, what crop did you grow last season? Maize, cassava, beans, yams. We could put these questions into any order, and the way that they're ordered has no meaning. But let's look at an ordinal example. Let's ask a different question. What is the highest level of education that you have completed? In this case, again, we have categories: primary school, or secondary school, or university. But the order that they're in does matter. You can easily imagine going primary, secondary, to university. Or it could be in the other order. That would be fine as well. But you wouldn't jumble the order up. It makes sense that primary comes before secondary, comes before university. Another example of an ordinal categorical variable would be a Likert scale. You've probably seen this before. You've probably taken a survey that has something like this. Let's look at an example. What if I asked you, how much do you like this class so far? You could be asked to give a number. Give a number that indicates on a scale how much you like the class. It could be, let's say, from 1 to 5, where 1 means not at all, and 5 means a lot. In this case, this is a categorical variable. Each of these numbers stands for something. It represents something. 1 represents not at all. 5 represents a lot. The fact that the numbers are 1 to 5 doesn't really matter. It could be 10 to 15. It could be to 100 to 1,000. It doesn't matter what the numbers are. The numbers themselves don't have meaning, but the order does, and the categories do, what the numbers represent. This would be an example of an ordinal categorical variable. Okay, what about quantitative data? I already alluded to this earlier, but let's look at it again. Quantitative data, this is data that consists of numbers that represent counts or measurements. Discrete, it comes into two categories, discrete and continuous. Discrete data is data that's either finite in number or is countable. Continuous data could, theoretically, take an infinite number of possible values that fit within a particular range of values. So let's just look at some examples. If we're taking some survey data of some farmers, I use a lot of farming examples. As you'll see, a lot of my research relates to small-scale agriculture in Africa. So I use a lot of farming examples. Okay, so a discrete example would be, we asked them, did you use fertilizer on your crop last year? 1 indicates yes, 0 indicates no. Very common, discrete. A continuous example would be, how much fertilizer did you use? In this case, they would have to give a number, and that number could be anywhere from 0 to infinity. So that would be a continuous variable. Okay, with that said, let's jump into Stata and take a look at what our data looks like. All right, I'm going to open up Stata. Let's see, here we are. All right, I hope that you've watched the Stata tutorial. I'm not going to talk through anything. If you're confused in what I'm doing, go ahead and pull up the Stata tutorial and watch that first. You can pause this video and watch that one. So here's my main screen. I'm going to open up the data set that is called wages, and we're going to look at that. All right, wages. If you remember from the Stata tutorial, we added the labels. If you haven't watched the Stata tutorial, go ahead and do that. All right, all I want to do right now is I just want to look at our data. I just want to look at data, and I want to think about the different types of data that we just talked about. So here, I've just opened a data set, and here we go. We've got 6 different variables. Now, just looking at that, pause for a moment and see if you can think of what kind of data these different variables are. Okay, so we've got 3 variables here, and what do these represent? We could even look at our label and see. Wage is hourly wages measured in dollars. This looks like a continuous variable to me. It probably could go from anywhere from 0 to infinity, at least in theory. What about education? Let's see, education. Education measured in years. That means this is the number of years they've been in school. This one's a little bit more tricky, but we would typically consider this to be continuous. They could have anywhere from 0 to an infinite number of years of education. In theory. In practice, I'm sure they probably don't go very high. We could take a look at what the max was in a moment. What about experience? Experience, again, continuous variable. It could go anywhere from 0 to, theoretically, infinity. Experience, let's see, measured in years. Okay. Non-white. Now this is a variable. Is equals 1 if the person is not white, and equals 0 if they're white. Aha, this one is a discrete or a dummy variable. What about female? Female, the same story. Equals 1 if they're female, equals 0 if they're male. Married, another variable, a dummy variable or discrete variable. Equals 1 if they're married, equals 0 if they're not. Okay, so in this data set we have examples. We have examples of continuous variables. These are continuous variables. And we have examples of binary variables. These 3 are binary variables. We notice in this data set we don't have any categorical variables. I'd like you to think about what a categorical variable might look like in a data set. And think about it. Take your time to think about what would a categorical variable look like in a data set. Okay. Now also, I might just take a moment. Let's just go through the data a little bit here and just make sure we're really familiar with looking at a data set. So, like we said before, these are variables. And then each row is an observation. So that means 1 indicates a person. Person 1, let's figure out what's person 1 like. Person 1 earns $3.10 an hour. Person 1 has 11 years of education. They have 2 years of experience. They're white, female, and not married. Person 2, what's person 2 like? Person 2 makes $3.20 an hour. They have 12 years of schooling, 22 years of experience. They're white, female, and they're married. We could do that for all of them, but hopefully that illustrates kind of what we're looking at in the data set. Okay, let's go back to the lecture. We'll come back to the data set in a minute. Hopefully that gives us a nice just familiarization. What does data look like? Now, with that kind of in our back pocket, let's do a statistics review. Okay. Now this might be kind of a quick statistics review. If you think you need a little bit more review, you can come and talk to me. And you can also look at the Khan Academy statistics review videos that I also have on my YouTube channel. I've linked to it on my YouTube channel. And I've also, I also can provide you some other materials. So come and talk to me if you'd like a deeper review of statistics. But okay, we're going to do a quick review of just some basic concepts. Okay, when we're doing statistics, what is statistics? Statistics is where we use data and we use mathematics to answer to test hypotheses, to study research questions. Statistics is kind of the foundation for econometrics. Econometrics is where we use statistics, statistical analysis, to try to answer economics questions. Now, one thing that we do in statistics, the power of statistics is, let's say we want to study, we want to describe, we want to study an entire population of people. Okay? But we can't collect data on an entire population of people. And so we can use statistics to learn about a whole population of people using just a sample. Okay, so then let's kind of hammer away these concepts. So when I talk about a population, what I mean is the collection, the complete collection of all the individuals or all the observations that I might want to study. Let's say I want to know something about all of the farmers in northern Ghana. I've done some research in northern Ghana, and so I typically will use examples from northern Ghana. So let's say I want to know information about all the farmers in northern Ghana. It would be very restrictive for me to go to northern Ghana and collect data on everyone. So instead, I will use a subsample. And I'll look at that sample, that collection of individuals, and I will use that information to try to draw conclusions about this population. Now we would say that whatever's true about the population is the actual truth that we want to know. But like I said, we rarely have data on the whole population. We think of another example. Let's say we want to know something about students here at Catholic University of America. The whole body of students, all the students at the university would be the population. But let's say that for some reason we can't collect data on the whole population. What we would need is we would need to take a sample population, some subset of the total population. So in our example here, we've got Catholic University of America students as our population, and the sample is, let's say, economics students. So we survey the economics students. So we have a population, and we use our sample to study the population. We collect data on a sample, some subset of the population. Okay, let's think about some basic definitions. I've alluded to some of these before, but kind of drive these home. A variable is a mathematical expression that can take different values. Okay? A random variable is a variable, mathematical expression that can take different values from a predetermined set of possible values. And they're drawn from this set of possible values randomly. So all of the variables in our data set, they're variables. They are mathematical expressions that can take different values for every observation in our data set. And they're drawn. That means the values that the variable might take in any particular situation are drawn from a predetermined set of possible values. Let's say income could be any number between 0 and infinity, for example. Okay. A probability distribution is a function that describes the probability of drawing particular values of a random variable. It describes the distribution of the different values. So an example, let's see, if I just wanted to use the word distribution here, let's imagine that we collected data on income. I said the distribution of income. The distribution gives us an idea of, well, how many people have a really high level of income, how many people have kind of a moderate level of income, and how many people have very low levels of income. Let's say that I'm someone who's deeply concerned about income inequality. Usually I'm concerned about income inequality if a very small number of people have a very high amount of income, and a very large number of people have very low amounts of income. This would be if I'm concerned about the distribution of income. I'm concerned about a distribution of income where all the income is being held by a very small number of people, and then very little income is being held by most of the people in the population. But you could imagine a different distribution of income, a distribution of income that is more even, where the richest people have only a little bit more income than the poorest people. This would be a very even distribution of income. Okay, so probability distribution kind of gives us the probability of having different random variables. We'll make this a little bit more concrete in a moment. All right, then the last definition I want to make is an estimate. So I was alluding to this before, but I want to make it a little bit more clear now. An estimate, so in statistics, what we want to do is we want to know something about the population. Let's say I want to know the average income of farmers in northern Ghana. I want to know the average income. Well, maybe there's 10,000 farmers and probably a lot more. And I want to know the average of all of their incomes. But for let's say financial reasons or logistical reasons, I can't go and collect data from every single farmer in northern Ghana. So instead, I collect 1,000 data points. I collect data from 1,000 farmers, and I find the average income for those 1,000 farmers. This would be an estimate of the true population average. So this is something we're doing in statistics. We want to know the truth about a population. We want to know the reality. But we don't have information on everyone, so we can't know it for certain. Instead, we need to estimate it. We come up with some estimate, an educated guess, a data-driven guess of what it is. And that's an estimate. Okay. From a conceptual standpoint, that's an estimate. Okay, let's keep going. So I mentioned before, a random variable. It's a mathematical expression that can take different numerical values from a predetermined set of possible values. So we already looked at some data. This is just to drive it home. So you have individual I. Basically, we have 3 individuals in this data set. And then we have a random variable y. And each value, so this variable can take different values. So person 1 has y1, person 2 has y2, person 3 has y3. Okay. Each of these values occurs with some probability. There's some probability that when you go out and you ask students on campus what their income is, there's some probability that they will answer, $10 an hour. And there's some probability that they will answer $20 an hour, etc. There's some probability that you'll observe a particular value of a random variable. So that's just what I want to illustrate here. Now, a probability density function is a continuous, for a continuous random variable, is a function that defines the probability that a random variable will take a value within a particular range of possible values. It's basically a function that communicates to us the probability of getting different particular values. Let's look at a PDF. Let's look at a probability density function. This is a standard normal probability density function. Okay, this gives us the idea. This gives us an idea of the distribution of values within a population. So this is a standard normal. It's centered at 0. It's mean 0, and it has a standard deviation of 1. We'll define those in a moment. But basically, this graph, I think, gives us a good idea of what a distribution looks like. So there's a really high probability that if you pick the number at random from this particular set of values, there's a really high probability that that number that you pick is going to be somewhere around 0. It's going to be somewhere right around the middle, somewhere around the mean. Okay, and so the graph is higher there. Okay, you can see how this indicates a higher probability of picking a number around 0. Now, the probability of picking a number, let's say around 4, is very low. It's very unlikely. In this set of possible values, in this distribution, very, very unlikely to get a value way up here near 4 or way down here by -4. Okay, so this gives us an idea of the distribution, how the occurrences of the different values of a random variable occur within the population. Okay, and just to drive the point home on the estimates, what we do is we have a total population of people. We can't collect data on everyone, so we collect data on a sample, some subset of the population. And we use that information to estimate what is true about the total population. Okay. So let's go back to my example to drive this home again. Imagine that we want to study smallholder farmers in northern Ghana. And let's say the total population is 10,000 farmers. We can't collect data on all 10,000, and realistically it's much more than that. And so instead we go and we collect data on 1,000 farmers. It would be way too expensive to collect data on all 10,000. Okay, and so we have data on 1,000 farmers, and this is our sample. If we selected those 1,000 randomly from the 10,000, the characteristics of the sample would give us a good estimate of the population characteristics. It would be a good estimate. It wouldn't be perfect. There'd be some chance that our data is really, really different, that this particular subset, this particular 1,000 farmers is very different than the sample from the population at large. But it would be a good estimate of what's happening, of what's really true about the total population. Okay. Now, let's say that we've done that. We've taken a collection of sample data. We might want to just know some basic kind of descriptions of that data set. Just kind of some basic some things to just give us an idea of what the data's like. This is what we will eventually use for our descriptive statistics. Okay, so let's just review this. So basic statistics. What's the mean or the average? The mean or the average is the sum of all the values of a variable divided by the number of observations, the number of values in that variable. Okay, so the population mean, that's the average. That's the average of the total population. Let's say I want to know the average income for all farmers in northern Ghana. That would be the population mean, where n is the size of the total population, xi is some unique value of the variable x. Okay, and then what we do is we sum up those values. So if we have some data set here, we have different values for x. For the different individuals, we have 4 people in this population. What we would do is we would add up all the values, and then we divide by 4. That gives us an average of 7. Okay. Now, but we don't know what the population mean, so we have to estimate it using the sample mean. We collect data on some subsample. We calculate the average of the sample, and that will give us an idea, an estimate, of what the population is. Okay, so the sample mean. Again, this is just summing up the values in our sample and dividing by the sample size, the size of our sample, lowercase n here. Okay, so consider a sample of only 2 people. You add them up, divide by 2, you get 8. So 8 is a decent estimate of 7. Okay. So we'll note here that the average, sometimes we'll use the notation of what looks like it's an E and then a bracket of the variable. So use this notation where this is the average of x, the so-called the expected value. Okay, this is notation that we might use. The average or the mean is the same thing as the expected value. So if you ever see E bracket xi, or E bracket some variable, that means it's the average of that variable, the expected value, same thing. Okay, so the mean gives us kind of an understanding of what we'd say the center of the data. We might also want to know how the data is distributed in the population. We want to know how different, how likely it is to get values that are really far away from the mean. We can imagine a scenario. Let's take our example of our farmers in northern Ghana. Let's say that the average farmer makes 5,000 Ghana cedis per year. We could imagine a population that has a lot of variation. So you go and you look at the population, the average is 5,000, but you have a whole lot of farmers that make 10,000, 20,000, 30,000, and you have a whole bunch of farmers that make 3,000, 4,000, or 2,000, 1,500. You have a lot of variation in the data. You could also imagine an example when there's very little variation in the data. Let's say the average is 5,000, but almost nobody makes 10,000 or even 6,000. That almost everyone in the population makes right around 5,000. In that case, it would be very little variation in the data. Well, we measure that using the variance. There's the population variance. This is the amount of variation in the variable xi in the population. And it's measured this way, where you take each individual observation of x, subtract the mean, square it, and then sum it all up and divide by n. But, as is typical, we don't have the population variance, so we need to estimate it, and we estimate it using the sample variance, which is basically the same thing as the population variance, but instead uses the sample mean instead of the population mean, and it's divided by the sample size minus 1. Okay. We don't use variance all that often, practically speaking, and we typically don't use variance very often because variance is measured in units squared, so it's just not very intuitive. Rather, we typically use the standard deviation. The standard deviation is just the square root of the variance. Okay, so the population standard deviation is the square root of the population variance, and the sample standard deviation, an estimate of the population standard deviation, is the square root of the sample standard deviation. The square root of the sample variance. Okay, the last concept, and this will be a very important one. I want to talk about the topic of the sampling distribution of the mean. This will be very important. So to think about this, we're going to do an illustration to make sure we're conceiving this correctly. But basically, this is what we have. We want to know something about the population. We can't collect data on everyone of the population, so we collect data on a sample, some subset. But every time we go and we collect a sample, we will get different characteristics. That sample will have different characteristics. If we go to northern Ghana and we collect a sample of 1,000 farmers, that sample of 1,000 will have a certain mean, a sample mean. But if we went and we collected data from, we went and collected another sample of 1,000 farmers, again, we would have a sample mean, the average in that sample, and that sample mean would be different. And every time we go and collect a sample of data from a population, we will get a new mean, a new sample average. Therefore, this sample mean is itself a variable. And it has its own distribution. There's some distribution of this variable, the sample mean. Okay, let's make this more concrete using a whole bunch of little examples of farmers. Okay, each one of these orange figures here is a farmer, and they have their tool here. And let's say that this is our population. All of these farmers are our population. Its population's in orange. Okay, and the population mean farm size. Okay, I'm looking at farm size. I was talking about income earlier. Now I'm talking about farm size. The average, the expected farm size for this population of farmers, we're just going to say is 15 acres. That's the true average. The true average is 15 acres. But I don't have data on the whole population. Instead, I need to collect data on a subset. And then I will use that to estimate the true population average. Okay, so let's say we go in and we collect data, and so here I'm labeling the people that we collected data from in blue. We've randomly selected these individuals to collect data from. Okay, so our sample 1 is in blue. Let's say for this sample of people, the sample mean is 14. All right, that 14, it's an estimate of the true population mean of 15. Okay, but let's say I went and I collected a different sample. This time, I'm collecting a sample in a different random subset of the population, and I'm indicating this different subset with green. So sample 2 is in green. This sample mean is 18. You see, the sample means are different. They're both estimates of the true population mean, but each of them themselves are different. We could do another example. Let's say this is another subset, another sample in red. And the average for sample number 3 is 15.5. You can see that every time we go and we collect a new sample of data, we're going to get a different sample mean. Which means that sample mean is itself a variable. It takes different values depending on which sample it is the mean of. Each of those are estimates. Okay. Now, because it's a variable, it has a distribution. And let's look at what that distribution looks like. This is called the sampling distribution of the mean. The sampling distribution of the mean gives us an idea of the probability of drawing, the probability that my sample mean will take any particular value. Okay, so this is the sampling distribution of the mean. This is the distribution of sample means. Now it turns out that the mean of the sampling distribution of the mean, that is the average of the sampling distribution, is actually the true population mean, 15. That means if I went out and I took an infinite number of samples from a population, and then I calculated all of their sample means, and I took the average of all of those sample means, the average of all of the sample means, the mean of the means, would be the true population mean, 15. Now, the probability of drawing any particular sample mean, or I'll say it a little bit differently, it is most likely you have a much higher probability of drawing a sample mean that is somewhere close to the true population mean than you do drawing a sample mean that's really far away from the true population mean. So where do our sample means come in? So the first subsample was somewhere down here, it was 14, and the next subsample was kind of a little far away at 18, and then the next subsample was really close at 15.5. And we could keep going. And if we kept drawing samples, from the population, what we would find is that most likely those sample means were going to be somewhere around here. But every once in a while, you'll have sample means that are way out here in the tails. Okay, so this is the sampling distribution of the mean. This is a very important concept. We're going to use this when we're looking at hypothesis testing next week, and we're going to use in the next lecture, and we're going to use hypothesis testing all the time when we do regressions. Now we might wonder, okay, if the mean of the sampling distribution of the mean is the population mean, sorry for all the means. If the average of the sampling distribution of the mean is the population mean, we might be interested to know, well, what's the distribution of the sampling distribution of the mean? That means, how widely dispersed is it? Well, for that, we will calculate what's called the standard error of the mean, SE of the sample mean. This is the standard deviation of the sampling distribution of the mean. Okay? And what it is, it's the standard, you would calculate this, you would estimate the standard deviation of the sampling distribution of the mean by taking the standard deviation of your data and dividing it by the square root of your sample size, square root of n. Okay, that is the standard deviation of the sampling distribution. We're going to run into standard errors all the time. They'll be very important. Okay. Now just to give us an idea, the higher the standard error, the more widely dispersed the sampling distribution of the mean is. So here is a standard error of 1, and the sampling distribution of the mean is very wide. That means it's less likely that you're going to get something right around the average, right around 0, and more likely that you're going to get something kind of really high or really low. And then it goes down. As the standard error gets smaller, it becomes more likely that you're going to get a value right here kind of in the middle, and less likely that you're going to get a value out here in the tails. Okay, with that, I want to introduce another concept, another convenient measurement that will be important as we begin to think about just kind of describing our data and begin to think about looking at impact or looking at the effect of one variable on another. We'll get to more of that later. But let's just talk about what a conditional mean is. Okay, the mean, like I said, is the average of all the values of a variable. A conditional mean is the average of a variable conditional on something else. So here I have a mock data set here. This mock data set has 4 individuals, so we have 4 observations. And we have a variable farm size, and we have a variable female. Okay, so for each individual, we know how big their farm is. So for this person, they have a 10-acre farm, and this person has an 18-acre farm, and this person has a 22-acre farm, etc. And then female, this is a dummy variable or a binary variable. Person 1 is female, person 2 is male, person 3 is male, person 4 is female. Okay, so if I said, what is the mean of farm size? We've already talked about that. All we do is we add these up and divide by 4. Okay, I have it written here, the expected value of farm size. Another way of saying the mean. The expected value of farm size, or the mean of farm size, is 13.5. But if I said the conditional mean, well, conditional on what? Let's say I wanted to know what is the average farm size, the mean farm size, conditional on the farmer being male. Okay, that would be, I want to take the average of the variable farm size for the people who are male. It's conditional on the farmer being male. So I would write that like this. The expected value of farm size, this vertical bar here means conditional on female equaling 0. That means that they're male. So the expected value of farm size, conditional on the farmer being male, is 20. That's a conditional mean. That'll be really important. And we can think about why that might be important. Let's say I just wanted to know, hey, do male farmers have more, do they have more land than female farmers? I might be interested in knowing that. Well, how would I know that? Well, I would calculate the mean of farm size for females and the mean of farm size for males, and I would see if they're different. If I ask, well, how much more land do male farmers have than female farmers? Well, what I would do is I'd calculate the conditional mean of farm size, conditional on being male, and the conditional mean, conditional being female, and then I'd subtract. And that will tell me the difference. And so you might be very interested to know, okay, on average, male farmers have this much more land than female farmers. In fact, we could probably do our conditional mean right here in our head. We know the conditional mean for male farmers is 20. What's the conditional mean for female farmers? So that would be 10 plus 4 divided by 2. That's 7. Wow. Male farmers on average have 13 more acres of land than female farmers. That could have some policy implications. That could be very interesting to us to know that. Okay, so it's important to have this concept of a conditional mean. Okay, another concept that's going to be very important to us is we might want to know the relationship between two variables. Now, we're kind of already getting at it with the conditional mean. We kind of want to know, well, let's say we want to know the relationship between farm size and female. There's some relationship between these two variables. Are you more likely to have more land when you're male than when you're female? But a direct way of measuring that relationship is to look at the correlation. The correlation between two variables. So just a quick definition. The correlation is a relationship or a connection between two things based on co-occurrence or a pattern of change. Two variables are positively correlated if when one variable increases, the other increases. Two variables are negatively correlated if when one variable increases, the other decreases. So for example, we might expect that land size and farmer incomes would be positively correlated. So that means as farmers have more land, they also tend to have more income. They're positively correlated. That might be important for us. We might want to know how land is related to incomes. If farmers that have more land have more incomes, that might influence our design of policy. Okay, another example would be, we might expect that time spent watching TV would be negatively correlated with your GDP, your GPA. The more time that you spend watching TV, the less time you spend studying, and the less time you spend studying, the lower that your GPA will be. Okay, so these will be negatively correlated. Now let's look at some exact measurements of correlation. Let's first look at covariance, which will be closely related, and then we'll go on to an actual measurement of correlation. So covariance, a measure of how strongly two variables covary with each other. So covariance can range from negative infinity to positive infinity, and the unit is of x times the unit of y. Okay, so the population covariance is the sum of any particular value of the variable y minus the mean of, variable x minus the mean of x times any particular value of the variable y minus the mean of y. You multiply them together, and then you sum that up and divide by n. A similar calculation for the sample covariance. But a more intuitive measurement of correlation is the correlation coefficient. This measures the strength of relationship between two variables. And it's not sensitive to the unit in which the data is measured. This is a really nice measurement of correlation, and it'll come back up when we look at in regression analysis and do our econometrics. The sample correlation coefficient, or the correlation coefficient in general, is going to be the covariance divided by the standard deviation of the variable x times the standard deviation of the variable y. Now, of course, in this case, maybe I need to be more clear. I'm looking at the relation or the correlation between some variable x and some variable y. So we could say x is farm size and y is income. So the correlation is going to give me how strongly correlated, how strongly related these two variables are. And we might expect that variables that are correlated with each other are going to be closely related. That if two variables are strongly correlated, that will indicate to us that they might have a real relationship, that they're really related in real life, just like we said with land size and farmer incomes. Okay. Now, with all of that said, let's go ahead and let's do some descriptive statistics in Stata. All right. Let's generate some descriptive statistics. Again, let's open up Stata. And so we have our data set. Let's just remind ourselves of our data set. We have wages, education, experience, non-white, female, married. Okay, these are our variables. And we have our main window here. Now what I'm going to do, I'm going to close this for now. Main window over to the side. And I'm going to open up a do file. Okay, and I'm going to give this do file a label. This is going to be lecture 1, descriptive statistics. All right. Now what I want to do, looking at Stata here, is I want to just kind of go through what we looked at in the lecture and make it tangible for us. How do we use this practically speaking? For many of you, the concepts that we've gone over are review. But now I want to perhaps make this tangible and relate it to how we might use it practically. Okay, so let's just kind of remind ourselves, what are some of the things that we want to look at? So this is our lecture. We want to look at, let's generate some descriptive statistics. So let's look at the mean, the variance, the standard deviation of some of our data. Let's look at, let's think a little bit about what the distribution of our data looks like. And let's look at some correlation between some variables. And let's look at some conditional means. And let's actually even, let's really make this practical. What we've done in this lecture so far, it might seem like it's, for those who've taken a statistics class recently, might sound like, okay, I know these things, but how could these be useful when we actually want to, do an analysis of some data? Okay, so let's do that here. Lecture 1, descriptive statistics, let's say, and initial analysis. All right, analysis. There we go. All right, so what do we want to do? We've got some data on wages, education, experience, ethnicity or race, gender, and family. So whether or not they're married. The first thing that we want to do in our data set, and then we're just going to label what we're doing, is generate some descriptive statistics. All right. We just kind of want to understand what our data is like. So let's do that first. There's a couple different commands you can use for this, but the best one is probably going to be what's called summarize. Summarize. It's summarize or summarize. There we go. No. You'll quickly find that I'm not a great speller. So this is a command, summarize. It's actually, you can shorten it, you can abbreviate it to just sum. What you would want to do, what summarize does is it generates some basic descriptive statistics. So let's say that we're doing an analysis and we want to know, let's say we want to know how being married is related to wages. If we are doing that kind of analysis, then we're just going to want to know, okay, what's our wage variable like? What's the average wage in this sample? What's the standard deviation? How are the wages distributed in the population? So let's look. Summarize wage. All right, I'm going to highlight this, click it, and there we go. We've got our output here. What are we looking at? Summarize wage. This gives us just some basic descriptive statistics of the variable wage. Here's the variable wage. Observation, we have 526 observations. This sample has 526 individual observations of wage. The average wage in this population is $5.9, $5.90 an hour, $5.91 an hour. That's the average. The standard deviation is 3.7. That's kind of how widely distributed the data is. The minimum value is 53 cents per hour wage, and the maximum value is $25 per hour wage. Okay, that gives me an idea about my data. I just have some general understanding. This can be really helpful. Okay, now let's say that I want to generate some descriptive statistics for all the data in my data set. I'm going to come down here. I'm just going to write this in a separate line. And now, like I said, you can abbreviate the command summarize, so I'm going to do that. I never write out summarize, as you can tell, because I couldn't spell it right. And I'm just going to list out all the variables in my data set. Non-white, female, and married. All right, now let's select that. If I do that, it's going to give me a nice table, a nice descriptive statistics table. This is the type of table that you're going to want to have when you write a research paper. If you write a research paper, the audience, the reader, is going to want to know just the general characteristics of your data. And so you might want to run a command in your data set that looks just like this, where you look at just what does the data look like for the variables in your data set. You could also find yourself in a situation where you have a lot of different variables and you don't want to look at all of them. But you pick a select few and you take a look. So let's look at what our output looks like here. We've got all of our variables. Let's see. We have all of our variables, all 6 of our variables here. How many observations there are? We have 526 observations for all of the variables in our data set. And we have the means. Okay, the average wage is 5.9. The average education level is 12.6. So the average is that these students have had a little bit more than high school on average. The experience level is on average 17 years. So they average 17 years of experience. Now, these are continuous variables, so these are really easy to interpret. I'm going to come down here in a minute. These are really easy to interpret. It's $5.90 an hour, 12.6 years of schooling, 17 years of experience. Okay, we can look at the standard deviation. All right, we can look at the min and the max. So the minimum level of education is 0 and the maximum is 18. The minimum level of experience is 1. So the person with the least amount of experience in the data has 1 year of experience. And the person with the most has 51 years of experience. Okay, so this is all pretty intuitive. Now the rest of our variables, these are dummy variables. They can take values of 0 or 1. You can see that when you look at the mins and the max. The min value is 0. The max value is 1. When you see this, you think, oh, these are dummy variables. These are binary, discrete variables. Okay, well, let's look at that. Non-white, okay. The average is 0.1. Now, it's not obvious what interpreting that means. What's it mean to say the average is 0.1? Well, what this means is that 10% of the population is non-white. Okay, that's how I would interpret that. Same thing with female. You come down here, female, the average is 0.4, basically 0.48. Well, that means that 48% of our population are female. Okay, we can do the same thing with married. We have an average of 0.6. That means that 60% of our population is married. Now, I said before that we might be interested in doing an analysis and thinking, well, how are wages related to being married? If we wanted to do that, it would be important for us to at least know the descriptive statistics of wages and of married. What are the average? What's the mean wage? 5.9. How many people in our sample are married? 60%. 60% of the sample are married. Okay. Now, let's do another way of generating a descriptive statistic. We can also do mean. Mean will give us a little bit of a different, just a little bit of different information. Let's do mean wage. Let's run that code. Okay. Now what this does is this gives me, again, the average wage, but now it reports to me the standard error. It reports to me the standard error. Now, if you remember, the standard error is the standard deviation divided by the square root of the sample size. Okay. And then it gives you a confidence interval, which we don't need to get into at the moment. Okay. Now I'm very interested. I kind of want to demonstrate to you, kind of prove to you that this standard error follows the equation that we looked at. So let's go back for a second. Let's look at that standard error formula. Let's see, where do I have it? Here we are. The standard error. Okay, this is going to be very important. The standard error is the standard deviation divided by the square root of your population. Well, let's just confirm that. Let's pull up a calculator. Let's see. Where do I got a calculator? There it is. Let's just confirm this for ourselves. Now, the standard deviation of the wage is 3.7. I'm just going to round it off. Let's see, 3.71 divided by the square root of, let's see, for the square root of the sample size. Let's see, how do I do this here? The square root of 5.26. Here we go. There it is. Let's see. Standard deviation divided by the square root of the sample size. Something is not quite right in my calculation here. Let's do this a little bit differently. Let's do this. 3.71, right? That's our standard deviation, divided by the square root of our sample size. Okay, let's cancel this. 5.26 square root. Here we go. So that's the square root of our sample size. Let's remember that. 22.93. All right, now let's go back. 3.71 divided by 22.93. And what does that give us? Here we are. 0.1617. There you have it. Standard error is the standard deviation divided by the square root of the population size, the sample size. Okay, so these are two different ways we can generate descriptive statistics. We might be interested in knowing the standard error, and if we are, we can use the mean command. And if we're interested in just the standard deviation, we can use the sum command. Now you might think, well, why are descriptive statistics important? Well, let me tell you a quick anecdote, a quick side story about why this is important. Very recently, I got one of my research papers accepted at a journal. Okay, and when I had originally submitted my paper for publication, so the way it works, you submit it to a journal, the journal will send it out to reviewers, and then the reviewers will send it back with comments that you're supposed to address. Well, when I sent it out, one of the reviewers that sent it back, they said, your data doesn't make any sense. There's no variation in your data. All of your standard deviations are really tiny. Your data doesn't make any sense. I don't want to accept this paper at the journal because there's no variation in your data. I don't believe your data. I don't think your data is any good. And when I read that, I was like, wow, what's going on? What's wrong with my data? So I went back to my paper and I was looking at the descriptive statistics table, and I realized that I had used the mean command to generate my average and what I had mistakenly put as my standard deviation. So I had a descriptive statistics table in my paper, and I reported the standard error instead of the standard deviation. And so that mistake almost cost me a publication. So it's very important. Someone reading your paper really wants to know how widely distributed your data is. Standard errors are really small compared to standard deviations. And so this difference is really important. Okay. Now, that's a quick anecdote. All right. So this is how we generate descriptive statistics in Stata. But let's say that we want to know a little bit more. Let's say we want to know, we want to have a better idea of how our data is distributed within the population. Okay, in this case, what I might want to do is I might want to generate a graph. Generate a graph that gives us an idea of what we might say is how the data is distributed in our population, the observational distribution, we might say. So we might want to, let's generate a histogram of our wages. This will give us how frequently the different wage values occur within the data. So let's look at that. This is kind of a observational distribution, or a observational probability density function. It kind of gives us an idea of how wages are distributed. There's very few people that have a very high wage. Very few people have a wage of 25. Nobody has a wage of 0. Most of our people have wages right around 3. Okay? We might want to, let's see, K density wage. What does this look like? We also might want to generate a smooth distribution. Okay, these are two different commands. I can use histogram or I can use K density. I like to use K density because it's a smoother curve. But basically what I have here is I can have two different ways of demonstrating the distribution of wages in my data set. So you generate this graph and you say, oh, okay, look, this is how the data is distributed. Very, very few people way out here, very few people down here, lots of people here. And we can go back, we say, what's our mean? Our mean's 5.9. So our mean is right around here in our data set for wages. You might, if you're doing a research study and you have a variable that's very important to your analysis, you might even generate a figure like this and put it in your research paper, because it gives the audience an idea, it gives the reader an idea of what your data looks like. Okay. Now we might also want to do that we could even do that for some of our binary variables. Let's say we want to do histogram, and let's do married. We said we wanted to look at married, so let's run that. This distribution function is binary. There's only 2 values, but it gives us kind of the probability of the different ones. Okay. Oh, okay. All right. Now that's just kind of a review of what does it look like to generate an observational or a empirical, we might say, distribution. Let's look at another one. A histogram. Let's do education. What's education look like? So this is kind of discrete. We can see that there's a lot of people that have right around 12 years of education and a lot less people that have kind of out in the extremes. Now that might make sense. We have 12, when you graduate high school, you've been in school for 12 years. So in this sample, most people have just graduated from high school. All right, let's look at what it looks like if we smooth it out. K-density. All right, let's do that. And then let's see. Oh, I accidentally did wage again. Let's do education. There we go. All right, this smooths out the distribution. We can see, all right, the average is right here around 12, and it trails off at the end, and it trails off a little bit, although slower here. This gives us kind of the population, or the observational density. All right, now what else might we want to do? Now I said at the beginning of this section that I might want to, kind of want to get an idea of what, I want to get an idea of how related wages are with marriage. I might be curious, that might be a research question. Hey, do married people make more money than unmarried people? I might even want to go deeper. I might be really interested in say, does marriage help people's income go up? Like, hey, you should get married if you want your income to go up. Like, I might be interested, does marriage have a causal effect on income? Well, we'll talk about causation in a future lecture. But first, let's just get an idea. Do people that are married make more money than people that don't? How would we look at that? We can do the first steps of our analysis here. So let's do, we're going to do initial analysis. And we're going to look at we're going to look at wages and marriage. All right. And let's just ask our question. Do married people make more money than unmarried people? Okay, that's going to be our question. So our initial analysis. Well, how do we do it? Well, there's a couple of thoughts that come to my mind initially. One would be, I might be very interested in just doing a correlation. What if I wanted to calculate the correlation coefficient? So let's do that. The correlation coefficient between wage and married. Let's take a look. All right. This number right here gives you the correlation coefficient. It's 0.227. Now, you'll notice that it's positive. A positive correlation coefficient means that when you're married, you tend to have higher wages. That means that the variation in marriage indicates a positive, as you become married, your wages tend to be higher. If this was negative, that would mean that if you were married, you would tend to have lower wages. Let me do another correlation coefficient, not related to our immediate question, but just to kind of reinforce this idea. Let's do the correlation coefficient between wage and education. This is maybe a little bit easier to interpret because these are both continuous variables. Let's run that. We'll find, okay, it's positive. That means as you have more education, you tend to have higher wages. And the correlation coefficient is 0.4. Okay, but now I might want to go a little bit deeper here. Going back to our original question, do married people make more money than unmarried people? Well, we think we might have an answer here. We look at the correlation between wage and marriage, and we find that it's a positive correlation. But let's look at it a different way. We might even be able to quantify it. We might even want to say how much more income do married people receive compared to receive? How much more income do married people receive than unmarried people? Okay. Wow. Let's see. Don't think it's how you spell people. All right. Well, let's do a conditional mean. Now remember, we did mean wage, right? And we did mean married. All right, we've already done that. But now I want a conditional mean. I want to know what's the average wage. What is the average wage for people that are married? Let's do that. Average wage if married equals, now if you're married, I want to know if you're married. Let me take a note here. Average wage if you, average wage for married people. All right, well, married people here. All right. So you're married, that means the married variable equals 1. So the mean wage if married equals 1. All right, and then I'm also going to want to do the same for unmarried people. All right, average wage for unmarried people. So that would be when marriage equals 0. So this will be the wage, but only for people that are married. All right, let's take a look. The average the average wage for people that are married is 6.6. And there's 320 married people. Let's look at the average for unmarried people. The average for unmarried people is 4.8, 4.9. And there's 206 unmarried people. If we just compare the means, we can say, look at that. The mean wage is higher for married people than it is for unmarried people. We can even calculate the difference. And let's just round it off. 6.58. Let's see, 6.59 minus 4.86. Okay. On average, married people tend to make $1.73 per hour more than unmarried people. Now at that step, I might ask, do you think that marriage causes people to make more money? Now we can look at this and we can say, okay, married people make more money than unmarried people. But does marriage cause them to make more money? Or maybe there's another reason why married people make more money than unmarried people. Just think about that. Okay, so with that, we will conclude lecture 1. Let's go ahead. I'm just going to save the lecture and I'll post this on Blackboard, lecture 1. Okay, I might give it Descriptive Statistics. Okay, I'm going to save that. And that will be all for today. Thank you so much for listening, and I hope that you have an excellent day.